In mathematics, the remainder is the amount left over after performing some computation. In arithmetic, the remainder is the integer left over after dividing one integer by another to produce an integer quotient. In algebra, the remainder is the polynomial left over after dividing one polynomial by another. The modulo operation is the operation that produces such a remainder when given a dividend and divisor. Formally, it is also true that a remainder is what is left after subtracting one number from another, although this is more properly called the difference. This usage can be found in some elementary textbooks. Colloquially, it is replaced by the expression, the rest, as in, give me $2 back and keep the rest. However, the term remainder is still used in this sense when a function is approximated by a series expansion and the error expression is referred to as the remainder term. Integer division. If A and D are integers, with D non-zero, it can be proven that there exist unique integers Q and R, such that A equals QD plus R and 0 are less than D. The number Q is called the quotient, while R is called the remainder. See Euclidean division for a proof of this result in division algorithm for algorithms describing how to calculate the remainder. The remainder, as defined above, is called the least positive remainder or simply the remainder. The integer a is either a multiple of d or lies in the interval between consecutive multiples of d, namely, qd and d. At times it is convenient to carry out the division so that a is as close as possible to an integral multiple of d, that is, we can write A equals kd plus s, with s, d, 2, for some integer k. In this case, s is called the least absolute remainder. As with the quotient and remainder, k and s are uniquely determined except in the case where d equals 2n and s equals plus or minus n. For this exception we have A equals kd plus n equals d, n. A unique remainder can be obtained in this case by some conventions such as always taking the positive value of s. Examples. In the division of 43 by 5 we have 43 equals a times 5 plus 3, so 3 is the least positive remainder. We also have 43 equals 9 times 5 to 2, and minus 2 is the least absolute remainder. These definitions are also valid if d is negative. For example, in the division of 43 by minus 5, 43 equals times plus 3, and 3 is the least positive remainder, while 43 equals times plus and minus 2 is the least absolute remainder. In the division of 42 by 5 we have 42 equals 8 times 5 plus 2, and since 2 less than 5 halves, 2 is both the least positive remainder and the least absolute remainder. In these examples, the least absolute remainder is obtained from the least positive remainder by subtracting 5, which is d. This holds in general. When dividing by d, either both remainders are positive and therefore equal, or they have opposite signs. If the positive remainder is R1, and the negative one is R2, then R1 equals R2 plus d. For floating point numbers, when A and d are floating point numbers, with d non-zero, A can be divided by d without remainder, with the quotient being another floating point number. If the quotient is constrained to being an integer, however, the concept of remainder is still necessary. It can be proved that there exists a unique integer quotient q and a unique floating point remainder r such that A equals qd plus r with 0 are less than d. Extending the definition of remainder for floating point numbers as described above is not of theoretical importance in mathematics. However, many programming languages implement this definition. See modulo operation. In programming languages, while there are no difficulties inherent in the definitions, there are implementation issues that arise when negative numbers are involved in calculating remainders. Different programming languages have adopted different conventions. Pascal chooses the result of the mod operation positive, but does not allow d to be negative or 0 *d plus a mod d is not always valid. C99 chooses the remainder with the same sign as the dividend. A. Perl, Python, and Common Lisp choose the remainder with the same sign as the divisor. D. Haskell and Scheme offer two functions, remainder and modulo. Place I has mod and rem, while Fortran has mod and modulo. In each case, the former agrees in sign with the dividend, and the latter with the divisor. Polynomial division. Euclidean division of polynomials is very similar to Euclidean division of integers and leads to polynomial remainders. Its existence is based on the following theorem. Given two univariate polynomials A and B, not the zero polynomial, defined over a field, there exist two polynomials Q and R which satisfy, where deg denotes the degree of the polynomial. Moreover, Q and R are uniquely determined by these relations. This differs from the Euclidean division of integers in that, for the integers, the degree condition is replaced by the bounds on the remainder. R. The similarity of Euclidean division for integers and also for polynomials leads one to ask for the most general algebraic setting in which Euclidean division is valid. The rings for which such a theorem exists are called Euclidean domains. But in this generality, uniqueness of the quotient and remainder are not guaranteed. Polynomial division leads to a result known as the remainder theorem. If the polynomial f is divided by x, k, the remainder is the constant r equals f.